Hello everyone. Today we are going to learn convex sulfate. So this is best known as a dynamic programming optimization trick, but there are problems where you will need to use convex sulfate without the need to use a DP. So we're going to learn this today, but before going to the actual convex sulfate, there are some prerequisites. So I will go over them really quick. At first, what is a convex polygon? So a convex polygon will be a polygon where all the internal angles are less than or equal to 180 degrees. So if we take a look at all these internal angles, they will be less than or equal to 180 degrees. But for the polygon on the right side, this angle is greater than 180 degree. So this is not a convex polygon. Okay, and this is a convex polygon. Okay, so now what is a convex hull? So when we are talking about a convex hull, we are dealing with a bunch of points. So these red dots are those points. So the convex hull of this point will be the convex polygon, which has the smallest area and it covers all the given points. So here you can notice that this blue polygon is the polygon which covers all the points and has the smallest area. If we took this polygon, let's say for example, this is another polygon which covers all the points, but this does not have the smallest area. If we take this side, then it will have the smallest area. So this is the convex hull of these points. Now a convex hull, so this is a convex hull. This can be divided into two parts. One is the upper hull and another one is the lower hull. So we are going to use this later. So now another thing we need is what a line is. So a line can be expressed using this equation, y equal to fx equal to mx plus c. So if we know the values of m and c, then a line can be uniquely defined. So by using the values of m and c, we can know what the line looks like. So for a value of m and c, this can be the given line. So here we have two variables, x and y. So if we know the value of x, let's say for example the value of x is a, then we can determine the value of y, which is just ma plus c. So we replace the variable x with the value a. So we can know the value of y from this. So what is the visualization of this? So if the line is this and the value of x is a, then we can draw a line x equal to a, which will be parallel to the y-axis, and the point where these two lines intersect, the y coordinate of that point will be our desired y. So the distance from x-axis of that intersecting point will be our desired y. Yeah. So another thing that we need is ternary search. So ternary search has a special property. If the graph of a function, so let's say the function is y equal to f of x, so it is a function of x. So as x progresses, if the function looks like this, so it increases up to one point, then decreases, so it will have a maximum value, or the function decreases at first, then it increases, it will have a minimum value, then the maximum value for the first graph and the minimum value for the second graph can be determined in logarithmic time using ternary search. So I guess you guys are familiar with how it will work, so I'll not go into more details, but just know if the size of this is n, then we can determine the minimum or the maximum value in O of log 1.5 n. Okay, now we can move to the actual convex sulfate part. So let's first learn about a problem. The problem says that we have n lines, m and mi and ci. As I said earlier, a line can be uniquely determined if we know the value of m and c. So we have n such lines. So in the picture below, you can see the lines in green color. So we also have q query points x of j, and for each query the answer will be the minimum value among all the values of this. So for all the lines we have mi and ci, and in that line we are going to put our queried point xj, and for all the lines we need to return the minimum value of this yi. So yeah, so let's take a look at the problem visually. We are given some lines. Here we have the lines in the green, and if the queried point is xj, then if we draw the line x equal to xj, so this will be parallel to the y-axis, then you can see that this line will intersect with all the other lines at some points, and the minimum value that we are looking for, the minimum value of yi, will be the minimum value, will be the lowest point of all these intersecting points. So for all these points intersecting with xj and some other line, whichever point is the lowest will have the minimum y value, and that is what we are looking for. So the answer will be the y value of this point. Yeah, so we are looking for this. So at first you can notice that there are some unnecessary lines. Let's take a look at line number 4. None of the queried points will get the minimum value in line number 4 because if our queried points are in this range, then they will all intersect with this line. So this will give us the minimum value. This line will give us the minimum value for this range. If the queried points are in this range, so they will intersect with this line, and this line will give us the minimum value. Similarly, if the queried points are here, then this line will give us the minimum value. If the queried points are here, then this line will give us the minimum value. So two things to notice here. Line number 4 will never give us the minimum value. Same for line number 5, it will never give us the minimum value. So this is the first thing. There will be some unnecessary lines that we can remove. And second thing to notice is that how our y values will look. So if you take a look at the intersection points for all the x's, you can notice that all these segments of the lines will form a convex hull here. So this is what our hull is going to look like. So all the necessary segments will form a upper hull here. So I visualized it here. So all these parts will form an upper hull like this, where this part is from the line 1, this part is from the line 2, this part is from the line 3, this part is from the line 6. So all these necessary segments will form an upper hull. So this is when we want to find the minimum value. But let's say our goal was to find the maximum value of y. So then you'll notice that let's say our queried point was in this range, then the lines will intersect with this segment. If the queried points were in this range, they would intersect with this segment. So these segments will give us the maximum value, because these points here will not give us the maximum value. So for this case, we are going to get a lower hull like this. So for both the cases of minimum, finding the minimum and the maximum, we are going to get convex hulls. So this is our observation, and see what we can how we can use this observation to find the minimum or maximum value very fast. So as I said, there will be some unnecessary points. So here 4 and 5 were unnecessary. So here we removed those unnecessary points. So if you take a look here, there aren't any unnecessary points. I just drew the necessary lines here. So there aren't any unnecessary lines. Sorry. So I just drew the necessary lines here, and here the convex hull formed by these lines looks like this. Okay. Now let's consider a queried point xj, and the red dots are the points where xj and the other lines will intersect. So we are interested in the minimum among these intersection points, so the lowest value. But we can notice a property here. For line number 3, we can notice that the intersection point is the lowest. So this will obviously, y of 3 will give us the answer. But if we take a look at line number 2, this is the intersection point. This is greater than y of 3, and if we take a look at y of 1 here, y of 1 will intersect here. This is greater than y of 2. And similarly, if we take a look at y of 4, the intersection point is here. This is greater than y of 3. And if we take a look at y of 5, the intersection point is here. This is greater than y of 4. So you can notice a pattern here. As you move from the lowest point and as you go outwards, so these points are sorted in a non-increasing order of slope here. So non-increasing order of m, I sorted all these points. So as you can see, the line 1 has the lowest slope, then line 2, line 3, line 4, and line 5. So if we order the lines in non-increasing order of slope, then the distances, so the distance of the intersection point will be like this. There will be a minimum point for some line, minimum value for some line, and as we go to the left of it, the distance will increase, and as we go to the right of it, the distance will also increase. So you can notice that the graph will look like this. For some point, we will get the minimum value here, and as we go to the right, the values will increase, and as we go to the left, the values will also increase. So this gives us the opportunity to use ternary search here. So if we get rid of all the useless lines, and if we only keep the useful lines, and if we order them in non-increasing order of slope, then we can use a ternary search to find the minimum value for some queried point. So this is the actual convex hull trick part. So here we are using the property of the convex hull, and we are using ternary search here to find the minimum value. So this is the convex hull trick. Okay, so now we are going to understand how we can create the hull. So how we are going to create the convex hull. So at first we are going to take all the lines and we are going to sort them in non-increasing order of their slope, like this. So the line with the largest slope will be at first, and the line with the smallest slope will be at last. So here we have the lines here, and we ordered them in non-increasing order of their slope. So this line has the largest slope, then line 2, then this line, then this line, then this line, and then this line. So we sorted them at first. Then we're going to add each line one by one. Let's say we have added 2 lines. We're going to add the third line here. So the third line can be like this. I'll use another color here. So the third line can be like this, or like this, or like this. But the third line will not be like this. because then the slope of this will be greater than this. And as we have already sorted the lines, so we will never get a line like this. And if we get a line like this, there will be two basic cases. One case will be when the third line is like this, and another case is when the third line is like this. So I will describe what the two cases are. So if the third line is like this, then you can see that this line is needed in our convex hull. So the convex hull will be like this. So this is from line 1, line 2 and line 3. So second line and third line both are needed in our convex hull. But if the third line is like this, so the previous hull was like this, but after the addition of the new line, the hull is going to look like this. So for this case, you can notice that the second line will become useless. So we don't need the second line in our convex hull anymore. So we are going to remove the second line and add in our third line. So how are we going to decide if the last line is needed or not? So we can decide that by just taking a look at these two cases. We're going to take a look at the intersection point of line 1 and 2 and line 2 and 3. For this case, you can notice that the intersection point of line 1 and 2 is to the left of the intersection point of line 2 and 3. If this is the case, intersection of 1 and 2 is in the left of intersection of 2 and 3. So we are going to need both the second lines and the third line. So we just add the new line here for this case. But if the intersection of line 1 and 2 is to the right of the intersection point of line 2 and 3, then we do not need the last line. So we can get rid of the second line here and add the third line. So this is the case. Then the intersection of 1 and 2 is the x value of the intersection of 1 and 2 is greater than or equal to the x value of intersection of 2 and 3. So these are just the two cases. But let's say we're adding in the line 4, and this was our convex hull previously, line 1, 2 and 3. But if we add in the line 4, both the lines 2 and 3 will become useless. So the new hull will become like this. So from here, so we cannot just get rid of the previous, we cannot just check the previous line to if we see we need to exclude it or not. We're going to check the last 3 lines as long as there are at least 3 lines. So we're going to check 2, 3 and 4 at first, then we're going to get rid of line 3. So fourth line will become the third line now. Then we're going to check 1, 2 and 3, and again we're going to get rid of line 2. Now we'll have just line 1 and 2. So this is going to be the convex hull line. So we need to do it as long as there is a bad line. Okay, now we're going to come to the calculation part. So how are we going to figure out the intersection points or the x coordinates of the intersection points? So if these are the 3 lines, so let's say line 1, 2 and 3, then if we solve line 1 and 2, then we can figure out the x value of line 1 and 2 of their intersection. And if we solve these 2 lines, then we can figure out the x coordinate of their intersection. So let's solve the first 2 lines. We can say y is equal to y, so m1x plus c1 will be equal to m2x plus c2. So this is what we wrote here. So this is m2. Okay. So we can bring m2 to this side and c to this side, so like here, and we can take x common here. So then we'll have m1 minus m2, and m1 minus m2 can be divided to this side. So then finally we get the value of x. So this is the intersection point of x. So this will be c2 minus c1 by m1 minus m2. Similarly, we can figure out the intersection point of line 2 and 3. So it will be c3 minus c2 by m2 minus m3. So we just need to check if x12 is greater than or equal to x23 or not. So we just need to check this. So if this is true, then we're going to get rid of the last line. Otherwise, we're not going to do anything and add the current line. So, but there is a problem. As you can see, we're going to use division here, and if we use division, we need to use floating points here, and that might cause precision errors. For that reason, we can avoid floating point division by just multiplying. So we can just take this here and take this here, so we can just multiply them. So then we can just check if C2 minus C1 times M2 minus M3 is greater than or equal to C3 minus C2 times M1 minus M2 or not. But there is another problem. The value of C and M can be really large. They can be as large as 10 to the power 18. So their multiplication will cause the value of 10 to the power 36. So as you guys know, this will not work if we use long longs. So we need to use int 128 here. So in int 128 we can store the value 2 to the power 127 minus 1. This is the maximum value that we can store in it. So this is large enough for 10 to the power 36. So if we just use this, it will be good enough. Okay, so now before moving to point 9, let's take a look at the code at first, how we are implementing it actually. So this here is the code. At first we have a structure of a line. So we just need M and C, and we have a constructor, and if we pass the values A and B here, we'll assign A to M and B to C. Now we have another structure for the actual CHT. Here we have a vector here. We have a vector of lines, and this vector will hold the convex hull for us. So this will actually hold the convex hull that we need to find the minimum or the maximum value. So let's take a look at the add function now. And if you notice the bad function, it's just showing red because I don't have 64-bit C++ installed, so that is why. But if you run this code in a 64-bit system, then it will work. So let's just take a look at the add function. At first we are going to add the current line to our convex hulls. So for example, line 1 and 2 are already in our convex hull. So this is the line 3. So we're going to add this line to the vector now, and then we're going to check the last 3 vectors. So if the vector is like this, so there are lines here, so we're going to check the last 3 lines at each step. So we took a variable size. It is going to hold the size of the vector. So as long as the size is at least 3, and this is the last 3 lines, and as long as they are bad, so I'll go to the bad function. But if it is bad, so we're checking bad using the equation I described here. So this is the equation. If the 3 lines follow this equation, this inequality, then we need to remove the second last line. So we're erasing the second last line here, and we're just decreasing the size by 1. And let's take a look at the bad function. This is a Boolean function, and in it we're calculating 2 variables A and B. So A will contain C2 minus C1 times M2 minus M3, and B will contain C3 minus C2 times M1 minus M2. So these are exactly the values that I said here. So we just need to check if A is greater than or equal to B or not. So that is what we're returning here. A is greater than or equal to B. So this is how we're going to add a line to our convex hull. And if we take a look at the query function, at first we have another function here which is called val, and in it we're going to pass a value x and an index. So this index is going to be the index of a line. So by accessing v of int, we're accessing a line, and if we do v int dot m, that means we're accessing the m value of that line. So we're just essentially doing m into x plus c. So we're getting the y value for some x on a line. So this is what this val function is going to return to us. And if we take a look at the query function, we're going to run ternary search here. So we have L equal to 0 and R equal to the size of our convex hull minus 1, and we're going to run ternary search here. We're going to calculate two mids, mid 1 and mid 2, and if the value of mid 1, so if this is the y value for the line which is mid 1, and this is the y value for the line which is mid 2. So if we get a lower value for mid 1, then we want to go to the left, otherwise we want to go to the right. So we want to go towards the lower value. So this is what we are doing here. If the lower value is to the left, we're setting r equal to mid 2 minus 1, otherwise we're setting L equal to mid 1 plus 1, and we're always taking the minimum value in our answer variable. And finally, after we're done with the ternary search, we can just return the answer. Yeah, so this is the query function. So this is all we're doing inside our CHT. Okay, now let's take a look at another example. So here is the example. So we have another problem, I'm sorry. So in this problem, we are given queries of two types. So we can add a line mc. So we're going to add a line y equal to mx plus c, and in the type 2 query, we need to find the minimum or the maximum value of y considering all the lines that we inserted earlier for this value a. So this is exactly the previous problem, but here we're going to add some lines, then we're going to query, then again we're going to add some lines. So you can say that we're adding lines on line, and if we want to do this, there are some conditions that we need to fulfill. If you remember what we did while creating the convex hull, we sorted the lines in non-increasing order of their slopes. So if we want to add lines here, we also need to maintain that property. The lines that are given to us in the query that we need to add needs to be sorted in non-increasing order of their slopes or non-decreasing order of their slopes. Then we can add the lines on line. Otherwise we cannot add the lines on line. It will just not hold the property that we are using to add a new line. So this is just the one property that we need to maintain to add a line on line. Yeah, so we will solve some problems where we need to add lines on line, and you will see that those problems will maintain this property, but the lines that we are adding are sorted in non-increasing order or non-decreasing order. So now let's take a look at this problem, and we're going to solve this using CHT. So this problem is frog 3, and this problem is from the educational DP contest which was held at Coder. So this is the very last problem, 26th problem of that contest. So let's see what this problem says. We're given two integers n and c. There are n stones with height h of I, and a frog is initially at stone 1, and he can jump from stone j to stone I with a cost of hi minus hj whole square plus c. This is the cost of jumping from one stone to another. So we need to figure out the minimum cost to reach the nth stone, and here the value of n can be as large as 2 into 10 to the power 5. So at first, let's figure out a slower solution. We're going to figure out a slower dynamic programming solution. So let's say these are the stones, and we're going to run dp here. So dp of I is going to denote the minimum cost to reach stone I. Min cost. And obviously the answer to our problem is dp of n, because we need to reach the stone n, and the base case is dp of 1 is equal to 0, because we are initially at stone 1, so we don't need any cost to reach there. So let's take a look at the transitions. If we want to calculate dp of I, let's say this index is the ith index, then we can jump from any lower index to this index. So we can jump from all these indices. So the transition will look like this for all j from 1 to I minus 1. So we're going to jump from j to I. So let's say this is j. So we're going to jump from j to I. So what is going to be the value of dpi? So we need to minimize the dp of I for all these j's. So dpi is going to be minimum dpi, and the cost of this jump will be h of j minus h of I whole squared plus c. This is the cost of the jump, and we are initially at jth stone, and we jump from jth to I. So we need to know the minimum value to reach the jth stone. So the minimum value to reach the jth stone is dp of j. So dp of I can be calculated like this, and the time complexity of this solution will be O of n squared. But this is too slow for n up to 2 into 10 to the power 5, and so we need to optimize this somehow. So let's try to simplify this equation. This is what we need to find the minimum value of. So let's try to simplify it. So hj minus hi square plus c plus, yeah, we can write this like hj square minus 2hj plus hi square plus c plus dp of j. This is h of I. Now hi squared and c is not dependent on j, so it will not change for different j's. So we'll just write them at first here, hi squared plus c, and we have a hi here. So yeah, this is the equation. So we are going to be left with h of j squared. Let's write this at first, plus dp of j and we're going to write this here minus 2 of hj into hi. So we just need to find the minimum value of this, because the left part is not dependent on j. But if you take a look at the part that we need to minimize, so this is the part that we need to minimize. So we can write it like this. So yeah, we can say that there are three parts. We can say this resembles m, this resembles c, and this resembles x. So we have some m and c values for all the previous indices. So if this is the array and this is stone I, and for all the indices j that are that are before index I will have some value of m and some value of c. So we'll have some value of m and some value of c, and for this value of x for hi we need to find the minimum value for some mi and ci. So this looks exactly like the problem that we learned to solve using CHT. We'll have some m and c's. What is happening? Okay, so we will have some m and c's, and for some x we need to find the minimum value of. Okay, so I just so this is going to be c. Yeah, this is going to be c and this is going to be m. My bad. So for some value of x we just need to find the minimum value of mx plus c. So this is exactly the problem that we can solve using CHT. So if we have inserted all the m and c for all the previous indices, then we can find the minimum value of this mx plus c, and then we can just add that to hi square plus c to find dp of I. Yeah, so for each index we can find dp of I in O of log n. So the total time complexity will be O of n log n. And here when we're done calculating the dp value of index I and we want to move to the I plus 1th index, then we're going to also add the m and c values for this index. So as you can see, we'll add lines on line here. So let's take a look at the code for this. So here we're taking n and c in input, and we're taking the heights of the stone input, and I took an object of the CHT structure. So at first we're going to initialize dp of 1 with 0, and we're going to add the line for that index 1. So as you saw here, the value of m was minus 2 into hj, so we have minus 2 into h1, and the value of c is hj square plus dp of j, so we have h1 square plus dp of 1. So we're adding this line to the CHT, and then for all the indices from 2 to n, at first we're going to calculate the dpi. So it is going to be here c plus hi square, so we have c plus hi square, plus we are going to query the minimum value for hi because hi is our x here. So now that we know the minimum value of dp of I, then we're going to add this line, this mici to our CHT. So similar to here, we have minus 2 into hi and hi square plus dp of I, and finally we can print out the answer, which is dp of n. So the thing that I talked about here, adding lines on line, for this problem we had another restriction where all the heights are going to be in increasing order. So if all the heights are in increasing order, if you notice here that the slopes of our lines here are minus 2 into hi. So if the lines are in increasing order or non-decreasing order, then minus 2 into hi is going to be in non-increasing order, so like this. So this was our condition to be able to add the lines on line, and this is fulfilled. So we can add the lines on line and correctly get our answer. Yeah, so this was convex solve trick. Thank you guys for watching. I hope you guys did understand. So solve some problems on this, and yeah, this is it. Bye.